Just to reintroduce myself, I'm Dave Brain. I'm a member of the MAVEN science team. I'm a co-investigator. I don't know exactly how many co-investigators there are, but it's on the order of 40, I would say. These are all scientists who are going to help MAVEN achieve its goals in some way. Many of these scientists are affiliated with a single instrument on MAVEN, either responsible for building it or responsible for using the data that will come from that instrument in some way. There are a handful of us, maybe on the order of 6 to 8, who are not uniquely assigned to a single instrument, but are instead tasked with doing certain science that will come from MAVEN in the end, using whatever instruments are necessary to answer those questions. And I fall into this latter category for my role on MAVEN. I wear a few other mats on MAVEN as well. I wear a few other hats on MAVEN as well currently. One hat that I wear right now is the science team member who is responsible for developing some visualization tools that the science team will use to study and analyze the data that are coming back. This consists of both software and a web page that the science team will use to interface with the data. And this is a unique challenge for MAVEN because unlike some other NASA spacecraft which visit a common object but do separate studies with the different instruments, MAVEN is really an integrated mission from start to finish. All of the instruments have to work together, which means we need to study the data from all of the instruments together in a combined fashion. So this presents some unique challenges for data analysis and data visualization. I also liaise with 2 other members of the MAVEN team. The 3 of us liaise with 3 members of the European Mars Express spacecraft to think about joint observations that our 2 spacecraft could do together. Let's see, I'm supposed to also talk about my background. I said a little bit yesterday that I like thinking about how planets evolve, not how they exist at one time and thinking of them in the steady state, but where are they going, where did they come from? And I especially like thinking about planetary atmospheres and how charged particles and magnetic fields can tell us something about how planets evolve. Let's see, what else for background? I'll skip ahead on that. Oh, my son is the oldest MAVENoid. This is a term that has come up in the team for people who are involved in the MAVEN mission who have happened to have children along the way. And my son, Calvin, is the oldest of the MAVENoids. So that's some background right there. Science. What science do I want to do with MAVEN? I'm watching my time. What science do I want to do with MAVEN? I picked out about 5 or 6 questions, but really if I had to pick one mission that I could do for my entire career, even before MAVEN was ever proposed, it would have been something like this. So I'm interested in everything that MAVEN will do. And I'll tell you 5 questions and maybe pick 1 or 2 to say more than a single sentence about. So let's start from small and go big. I'm really interested in aurora on Mars. Mars has patchy crustal magnetic fields, not a big global magnetic field like Earth. So on Mars you have aurora in unusual places that you're not used to thinking about on Earth. It's not aurora borealis or aurora australis, it's aurora spaghettialis or aurora messialis or something like that, and it's really neat to think about. I'm interested in studying aurora. On a slightly larger scale, I'm interested in studying the crustal magnetic fields of Mars and how they interact with the space environment. I think this is one of the most surprising and cool discoveries of the past 15 or 20 years in planetary science. To discover that Mars had strong crustal magnetic fields. It wasn't surprising that Mars possessed crustal magnetic fields, but that they were so strong. And the way that they interact with the space environment is really just unique. And Mars, in some ways, much more resembles the Sun than it does any other planet in the solar system in terms of its magnetic fields and what they do. And you can imagine these little magnetic field bubbles opening, closing, and particles rushing down field lines and getting trapped on field lines. It's really fun to think about. Moving up larger, I think my prime responsibility that I'd like to assign to myself on MAVEN is using the measurements of escape. Not the measurements of neutral particle escape. I'll probably focus on charged particles, ions, and not so much coming up with the escape rate, the number, but I'm more interested in how that escape rate varies today. And if you turn up the sunlight, how much does the escape rate increase? Turn up the solar wind, how much does that escape rate increase? To me, that's really the key thing that MAVEN will do that will allow us to extrapolate backward in time. If you can turn a knob and see how the system responds, then you have leverage to go back in time 4 billion years and understand how the system has evolved. So that's what I would like to do primarily with the MAVEN data. But this leads to me, for me, to some questions that are even bigger than that, and that I'd like to have underpin the remainder of my career. And these questions are number one, do magnetospheres matter? Janet raised this issue yesterday, and it was surprising for many of you, as it is surprising for many scientists. It's not a done deal that magnetospheres necessarily influence evolution of atmospheres any more than the lack of a magnetic field does, and I would like to tackle this problem, and I can explain that in more detail in the question and answer period if you'd like, why there's still a lack of resolution about this question, or a renewed lack of resolution about this question. And when you say, do magnetospheres matter, do magnetic fields matter, the bigger question for me is, are magnetic fields not required, as Nick was trying to say yesterday, for life, but are magnetic fields nice things to have for habitability of a planet? And this is a question that I think is fundamentally important, that I think we're capable of answering in the span of my career, and I think to tackle that too. And so in this sense, MAVEN, although it is a Mars mission, MAVEN is really using Mars for some of these bigger questions as the closest laboratory that we have for understanding planets and habitability and how they evolve around any star. And I'm done now.
Me? Okay. So, my name is Rob Lillis, like I said yesterday, and I'm also a co-I on the team on the 40 or so. And I also wear a couple of different MAVEN mats as well, one of which that didn't get
I'm not well.
Okay.
Just don't compare any funny ones.
Yeah, sure. So I have a hardware role, and that has been to be the deputy instrument lead for the solar energetic particle instrument. This is an instrument that, as its name implies, measures energetic particles from the sun. I've been working under an instrument lead down in Mars in that sense. And I also am a member of the science team, and in that capacity, the main role I think I've had is the organization of what's been termed the science closure effort. And this is really just the mechanics of how you get from the spacecraft measurements to the top level questions that MAVEN has, particularly concerning the measurement of atmospheric escape rates, both at the current epoch, through the various different channels, different types of atmospheric escape, and how you use that, as Dave most articulated, but how you see how the atmospheric escape rates change as you change things like the solar extreme ultraviolet flux, the strength of the solar wind, the direction of the interplanetary magnetic field, or the frequency of things like coronal mass ejections and other space weather disturbances. To see, give a good handle on how the escape rate varies with those different factors. Now you can make a more reliable, defensible extrapolation to early Mars history, and therefore your total estimate of the integrated escape over history can be more reliable. My background has been Mars most of my career. I've sort of split my time evenly between what I would call Mars aeronomy, which is studying the upper atmosphere, studying the ionosphere, studying space weather effects on the atmosphere, ionization from precipitating particles, how the weird and wonderful crustal magnetic fields affect those that ionization, and then of course what that ionization does in terms of electrodynamics and how currents flow, and also how particles are energized and therefore escape. So it's the sorts of things I'm interested in from the aeronomy and atmospheric standpoint are also linked to MAVEN science goals. The other half of what I've been interested in has been more geophysics. studying the cross-magnetic fields, and not just how they influence atmospheric escape and processes that affect that escape, but also the crustal fields themselves and what they tell us about the geophysical history of the planet, how impacts have demagnetized the crust, how volcanoes have also demagnetized the crust, things like magmatism, and what that can tell you about the history of the global magnetic field, which is something that's very important for the top level questions that Maven would like to answer. When exactly did the magnetic field disappear? And did it just disappear once? Could it have come back? Was it a slow, gradual decline? Was it rapid? And if we can get some better answers as to the history of the magnetic field, that'll help us in our extrapolation back in time in the context of the MAVEN project. I'm also, just like Dave said, I'm similarly interested in whether or not the presence of a global magnetic field actually has much of an effect on escape. Might it even make escape more efficient because of polar cap processes? And lastly, also the one other question I'm interested in is, once we do get a pretty decent idea of how much atmosphere has been lost to space from MAVEN, how does that answer fit into the broader question of Mars global climate history? As was mentioned yesterday by Nick, there was a lot of volcanism that went on at that time too, and that supplied the atmosphere. So it really complicates the whole question of Mars climate history because of the intersection at a very similar point in time of both the end of the era of giant impacts, which can erode atmospheres, the end of the era of substantial magmatism and volcanism, which can supply atmospheres, and the end of the global magnetic field, which may enhance or retard atmospheric escape. And so that intersection there makes for a very rich set of scientific investigations. So, thank you.
All right. My name is Jasper Halekas, and these guys took all the good answers already, so maybe I'll be short. I'm at the University of California, Berkeley. I'm the instrument lead for the Solar Wind Ion Analyzer, another very descriptively named instrument on MAVEN. And my interest in MAVEN is twofold, I guess. First, I'm very interested in making sure that that particular instrument makes the best possible measurements that it can and returns the best possible data products that all of the science team and the science community at large can use. So that's probably the thing that I've been spending the most time on in the last 3 to 4 years. And so a lot of my brain is taken over with things like circuit board layouts and electrostatic optics designs and things like that you need to make the instrument work. But I'm also a scientist, and I'm also interested in a lot of the same questions that Rob and Dave have talked about. In particular, what I'm interested in are the channels by which ions escape from Mars. You've heard a little bit yesterday about the basic design of the MAVEN mission. I like to think of the instruments on MAVEN as basically being in 2 groups with some overlap between them. There's one group which is measuring all the energy inputs to Mars from the sun, solar energetic particles, UV flux from the sun, solar wind ions, solar wind electrons. And there's another group of instruments which are measuring the products of the escaping neutrals, not directly but indirectly from UV spectrometry, and the escaping ions. But that's not enough. I mean, by making those measurements, you can measure what's coming in, you can measure what's going out, but you need to understand what happens in the middle, and that's what I'm interested in. And I think Janet gave you a little bit of an idea yesterday about how dynamic the Martian system is and how dynamic the energy inputs to the Martian system are. It's a dynamically driven system, and I'm interested in understanding how that works, particularly from the plasma physics side of things, because that's my training. But you can think of the solar wind as this hot ionized gas flowing at Mars, and it's carrying magnetic fields along with it. And you saw these amazing kind of spiral patterns that these magnetic fields form as they're coming out from the sun. Very, very, very dynamic. The flux varies by orders of magnitude. The magnetic field flops around in all different directions. Now imagine this hitting this obstacle formed by the gas, or in the Martian atmosphere, and the ionized components of that gas in particular. And things get very complicated indeed as these magnetic fields wrap and flap around the obstacle formed by the Martian ionosphere. And of course, there are crustal fields on Mars, which makes it even more complicated yet, because these crustal fields poke up through this ionospheric obstacle, and they're rotating around every day with Mars. And so Mars is presenting a constantly changing face to this energy input from the solar wind. And so I'm really interested in understanding how that interface works and what comes out the back end. So I think I'll stop there.
Okay, I'm Joe Grebowsky. I'm a major role of happening mission along the COI, Science COI. I'm a project scientist. There's a requirement when NASA project manages a mission, they have to have a project scientist. If this was my proposal, like Bruce's, I'd be a project scientist and responsible for the whole mission. Because it's a PI mission. Bruce and I had to come to some sort of relaxed agreement. I guess basically I'm involved in the science planning work. We have an integral science planning network. Bruce being vendor is taking care of the spacecraft development. In terms of my background, I guess what I'm interested, I'll be a little more focused. They've explained all the general areas that it's an integrated mission. But I want to focus, my background has been on the production and dynamics or energetics of low energy particles, like atmospheric particles. I'm looking at the production from, well, I've done studies on the 3 terrestrial planets. Production came from photochemistry, produced the ions. It came from impact ionization of the auroral precipitation. We have it on Earth, we have aurora on Venus probably, and we have aurora on Mars. And also ablation products of meteors coming into the atmosphere actually produce layers. I've been interested in that. I've done other things, lightning on Venus and some ancillary things, some space shuttle experiments. But what I'm looking for in MAVEN, I'm more of the aeronomy type of person. I'm interested in what happens to low energy particles. And Janet gave a nice review that magnetic field could stop the solar wind, but if you didn't have a magnetic field, the ionosphere is where the solar wind would dissipate itself, so it's very important for the planets. On the day side, you have photochemical equilibrium in the main layer. It's a region, the sun's UV ionizes the neutral atmosphere. And locally, the major layers below 140 kilometers, it consists predominantly of molecular oxygen ions, O2+. But in that region, things don't move. It's chemical equilibrium. The collisions between the ions and neutrals are so great that the ions can't move. There's a trap there. It's a trap box. But as you go to higher altitudes, when the collision frequency is dropping, the ions can start moving. The O2+ can move. And as you go up in altitude, O2+ is no longer dominant. It's the single species, the atomic species O+. So you can actually tell where you are in the ionosphere by the composition. Now what happens, we know there's dynamics going on. It's not just standing still on the base side. The Viking observations had indications that the top side of the ionosphere was flowing. And with Mars Express, which is still active and will be active during MAVENs, they've measured escape down the tail, where O2+ is the predominant escape product. And this means it has to come from very low down in the day side ionosphere. It can't come from high altitudes where O+ is dominant. So we have transport from the day side into the night side, accelerated down the tail from the ionosphere. And the second thing Mars Express has shown, on Venus, there are large gradients in the plasma density of the terminator. And you can look at it this way. Photoionization is occurring on the day side, and you have a sink of ionization on the night side, like a vacuum. So the plasma is going to move into the vacuum, and it's going to happen at the terminator. On Venus, this process, the gradients at the terminator, cause supersonic flows. But what happens on Venus, the flows go and has large gravity, and they come down to supply the night side ionosphere. On Mars, if you have supersonic flows developing at the terminator, they could be beyond escape velocity and they'll go down the tail. And this is one of the mechanisms that's been shown to do this. Some of the plasma comes down to supply the night side ionosphere, not as extensive as Venus does. So, and we have complexities because these flows going from day to night, if you have magnetic anomalies, plasma can't go through them. It needs a barrier. So my goal is actually to try to understand this. The static, we need to know the ionosphere composition, the neutral composition, to actually produce the ionosphere, and we have to know measurements of flow and thermal properties. NGIMS will supply neutral and ion measurements that we need. Static will supply velocities. MEX saw indications of these things, but MEX did not go down to lower altitudes. They had no magnetic field observations, and they had no composition measurements of the neutrals. So I think that's my goal. I'm just starting off on that. And I'm just hoping we find some discoveries to make things more exciting. I think we're all looking for that. Something new is going to happen. And we're going to be disappointed if it doesn't. Oh, I was also asked if I could ask one compelling question that you should ask me. And I'm going to put it this way. Why was there never an agronomy mission dedicated to Mars until now? And secondly, what's the consequence of having it now? For all other planets, we had agronomy missions.
So we don't get an answer?
No. Maybe you could tell me.
Talk to Congress.
So thank you all, and you can pursue that answer. So we're trying to get Michael Meyer on via Skype. He has confirmed he's going to get in touch as soon as he's able, so he'll be along shortly. In the meantime, I think we should just go ahead and you guys can start firing away questions and we can slot in them. So go
Joe, why was it never?
Actually, maybe Bruce had the answer. For example, the first mission we sent to Venus at Pioneer Venus Orbiter did an extensive around things, quite like what we're doing for MAVEN right now. And Bruce said yesterday, actually it was very insightful, we can't see the surface of Venus. Mars, you can see the surface. They're not distracted people. Yeah. In fact, there was a Japanese mission, Nozomi, that was going to go to Mars, but it was one of the ones that didn't make it. It's like the Martian. Nozomi.
And that was the
Planet B.
MI.
Yeah, but in terms of statistics, out of 30-some attempts to go to Mars, half of them failed. But none of them, except it was only the agronomy mission. We actually know the agronomy around the space shuttle better than we do the basic agronomy at Mars. And the consequences of this decision now, if we had had an agronomy mission before, chances are we wouldn't be rediscussing MAVEN.
So what are the consequences of having the second half?
We have MAVEN. If we had an agronomy mission before, I think of a very high probability MAVEN would never have been selected.
Let me add a comment to that, and I'll probably get in trouble as I walk down this path. But I think that we would never have been able to sell an agronomy mission on the basis of doing agronomy. The way we talk about it among ourselves is just bringing up the word, people fall asleep. And when we submitted our proposal for MAVEN, I insisted that the person who was assembling the proposal do a global search on the final text to make sure that the word agronomy had not crept in somehow. We pitched this not as an agronomy mission, but as a mission to understand the geology and the astrobiology. Things like where did the water go, where did the atmosphere go, tell us about the history of the geology and the history of the habitability. And I think this is something that resonated with the science community that was more interested in understanding the surface. Again, I'll probably get in trouble, but one of my colleagues, when we were starting to talk about this mission, came up to me and said, why would we ever want to do an agronomy mission when we could send another rover? And I think that reflects a lot of the attitude of the community. And we had to pitch this mission in the context of understanding the geology and the climate history, things that everybody does have an interest in.
Yeah, that's true. I've been involved, well, for terrestrial agronomy mission, there haven't been any for over 20 years, even at the Earth. MAVEN is taking measurements, comprehensive measurements over the entire globe, essentially over the entire globe. But they have one focus, actually the escape. On the Earth, if you have an aeronomy mission, you get measurements. It's going to be a circular orbit, something to the atmosphere all the time. You're going to get measurements all the time. But to get a proposal accepted nowadays for a mission, you have to have a focused topic. And if you deal with ionosphere, thermosphere, dynamics, on the Earth, they usually talk about the auroral impacts because that's where all the energy comes. But there's so many other things going on that it's very difficult to focus. So most proposals for terrestrial aeronomy don't have a focus that's acceptable. Whereas MAVEN with the escape has a very nice focus, and if you took the escape away, it'd be very difficult, as Bruce said, to just get a aeronomy mission, but it would be valuable. You'd have the same measurements, but it's that one focus, the escape.
I don't want to pretend to know whether putting the word aeronomy in or leaving the word aeronomy out of the proposal makes a fundamental difference, but I think that at its heart, the mission is a mission about evolution of the atmosphere, and that's what it is. And if aeronomy is the tool that you're using to get at that, then that's entirely appropriate, and that's what MAVEN is. It's an evolution mission.
Hey, question, does anyone know what aeronomy is?
Notice how my hand is not on it.
Well, actually, yeah, okay, it's the upper atmosphere, but it's also where ionization becomes important. It's not just the atmosphere, it's also ionization is important. Okay.
The word originally, actually, according to Andy Nagy, who explained this story once, apparently originally what we now think of as meteorology was called aeronomy. And for some reason that now escapes me, the name was essentially changed, or there were two different camps, and the word meteorology won, and the word aeronomy then became used to describe the upper atmosphere. Ask Andy Nagy, he'll be happy to tell you all about it.
I have a textbook if you want me to bring it in. It's right over there.
Does Tom pick?
Go ahead.
Or do we?
You guys can go ahead. Go ahead. I'm sorry, which one?
All right, mine actually builds on what we've just been talking about. And I may be oversimplifying, but what mission, satellite, or where's the data coming from for Earth in this that's related to this stuff that you're studying in MAVEN that will be able to compare or be thinking about some of these similar issues that, I mean, I know Mars is really different, but we've got to have looked at escape for Earth. You know what I'm getting at?
Yeah.
Okay.
Well, actually, Dynamics Explorer about 20 years ago, I actually measured the escape, and there's a Canadian spacecraft, EPOC, that's been sitting on a shelf for 10 years until they get a rocket to launch it. I've been told it's going to actually launch this year, but they said that last year. And this is dedicated for actually measuring the escape from the Earth's auroral region. On the Earth, because of configuration, you won't escape any place except up in the polar region where field lines open up and things kind of in space, and the solar wind could go in. But the EPOC mission is going to be dedicated to that.
See? Which? Oh.
EPOC, E-P-O-P, I don't know, it's an acronym.
Okay.
There's also a spacecraft called Polar that made a lot of measurements of ion escape. I think that's one of the sources of some of the numbers that Janet showed yesterday of the relative amounts of ions that escape from the Earth versus those that escape from Mars. That's an important data point as well.
And as Janet said too, I mean, you have on the closed magnetic field, and some of this stuff doesn't get out. It actually comes down, and it's a part of the radiation belts, the ring currents. They find that when there's a storm on Earth, the ring currents start being populated with O+ ions and not just hydrogen ions. It's indications coming from down below.
So can we hold the questions just for a bit? Michael, we're going to have you go ahead and do your intro. Can you hear me okay?
Yeah, I hear you just fine.
So here's Michael. And what we did is we did 5-minute intros for each of the other panelists. So if you can just go ahead and introduce yourself. I'm going to turn you around so you can see the participants.
Well, hi everyone. I'm sorry I'm not able to be there in person. It would have been a lot of fun, and but here I am and doing what I can and doing this on Skype. I hope this comes through okay, and I'm able to answer any questions that you might have. I am the lead scientist for the Mars Exploration Program and also the program scientist on Curiosity. The program itself has been challenging and a real, even a greater challenge the last couple of years, but it's also been exciting and fun, and particularly being associated with Curiosity has been just tremendous. The good news is that the Mars program is able to go forward. We have very successful missions ongoing now, and also we are planning to launch MAVEN, as you know, but also we are participating in the ExoMars programs with providing telecommunication capabilities on the Trace-Gap orbiter to launch in 2016. Also, we're providing a major instrument called MOMA that's able to detect organics on the ExoMars rover 2018. The Discovery program is also funding a mission to Mars called InSight, which will be a geophysical mission. That's launching in 2016. And then sort of the big news that's happened with the announcement, I guess, since AGU last year, is that we are going forward with a rover using the Mars Science Laboratory architecture, but with competing a different set of instruments, and the goal of basically looking for places that may preserve biosignature, whether there are any biosignatures there, and also catching samples. And this is to launch in 2020. We're in the process right now of writing an announcement of opportunity. And because of that, although I can answer general questions about what the 2020 mission will be, there'll be some details. I just can't mention anything because we are in the process of writing the AO. And any specific information has to be made generally available so everybody has an equal opportunity in terms of writing a proposal and for the fair and open competition. One of the things that might have come out in the meeting already, but just in case, it is a real pleasure for me to see that back in the mid-90s, we did a strategy called Exobiology Strategy for Exploring Mars. And this outlined, in a broad brush, the steps that should be taken when you're exploring another planet and trying to determine whether or not there was ever life. And the idea was that you have to learn about the planet, and you have to learn about regions specifically. You have to understand the environment before you actually have any hope of moving any further and determining whether or not that planet has biological potential, and whether or not it was there or is there today, or maybe nothing ever got started. And so it's a very step-by-step approach, and amazingly enough, we're actually still on that timeline in terms of steps that should be taken to explore another planet to determine its biological potential. I guess with that, I'll stop, and I'm more than happy to answer questions or discuss with the panel, and we'll see how this works out. Thank you.
Tom, why did you give us a giant bat?
We're complimenting your pterodactyl or bat, or if it's a bat.
No, it is a bat.
It is a bat.
Luckily, it's not alive.
So thank you, and I guess I'll sort of moderate the questions a little bit. Anyone want to start?
Very simple technical question, which maybe the definition of this term was given yesterday, but I saw it on at least 3 slides. Genes escape is on several of all. What does that refer to?
So Nick shows this picture of kind of a distribution of speeds of gases, and depending on what you do with the temperature of the gas and the mass of the planet and everything, different portions of that curve escape. That's genes escape.
So the thermal escape.
The thermal,
So when you have population gas, this is neutral escape. There are always some hot species that exceed the escape speed and they go out.
But genes?
Isn't genes in it?
That's the
Somewhere?
thing. The genes is the name of a scientist. And
That's what I was.
Genes escape and thermal escape are used as interchangeable terms. So just the intrinsic property that determines genes escape is the temperature of the gas. And of course, the mass of the planet plays a role there too, because big massive planets hold on to the gas more tightly.
This is like Avogadro's number. It's just, there was a scientist behind this.
Yes.
capital J.
So the crystal magnetic field, the little bubbles, look, this is a new one to me. Can you like explain how these are created? If we know, you said they actually poke out into the ionosphere. Like how high is this going? What's going on with these fields as far as we know?
Do you know what created the fields themselves?
What created them? How big are they?
Okay, so the sources for these fields are large volumes of coherently magnetized crust. Ferromagnetic minerals in the crust, various sorts of iron oxides, hematite, magnetite. There's a few other possible candidate minerals. We don't know exactly what minerals are responsible, but we know that in order to explain the strength of the crustal magnetic fields, you need really hundreds of thousands, if not millions, of cubic kilometers of coherently magnetized crust, i.e. all magnetized in a similar direction. Otherwise, if you have highly magnetized material, but the direction of magnetization is all jumbled, let's say, a piece this big is magnetized that way, and then a piece this big over here is magnetized that way, you won't see any signature of that as you go further and further away from it. But the strongest crustal magnetic fields on Mars can hold off the solar wind up to 1,000 kilometers above the surface. And so in order to get fields that strong, you need very large volumes of crust. And the only way that those could have come about is because Mars must have had a global magnetic field early in its history. And so geological processes allow the crust to acquire that magnetization. There's a few different sorts of natural remnant magnetization. That's the catch-all term used to describe naturally occurring magnetization. One is called thermal remnant magnetization or thermoremnant magnetization, and that's simply when you have a rock which is heated above its so-called Curie temperature, which is different for different minerals, and it loses its magnetic coherence when it is heated above that temperature. When it then cools again, it will acquire a magnetization proportional to the strength and direction of the magnetic field which exists at that time. So if we can see a feature such as a large impact crater, and we know that that impact crater happened at
I just muted it.
at 3.9 billion years ago, let's say, because we can count the number of craters on it. We know that the rocks in that crater were definitely heated above their Curie point, and so if we know that if we see a crustal magnetic field above that crater, we know that there must have been a strong magnetic field around at the time that that crater cooled after it formed. That's how we can date when the dynamo stopped working, because after a certain point, craters that are younger than about 4 billion years are not magnetized. Craters that are older than 4 billion years are magnetized. So crustal magnetic fields come from this process of natural remnant magnetization, most likely thermal remnant magnetization, and they can tell us about the history of the global magnetic field. And that leads into the main questions, of course, because that affects atmosphere.
So, and just a couple quick follow-ons for perspective. Mars has these magnetic fields in the crust that we call very strong, and they are very strong. As a matter of fact, Earth also has regions of its crust that are locally magnetized. And if you were flying with a spacecraft at 400 kilometers above Mars and 400 kilometers above Earth, measuring just the magnetic field from the crust, the fields that you would measure at Mars are a factor of 10 to 20 times stronger than the fields you would measure from Earth. But compared to Earth's global dynamo, it's about 1,000 times bigger.
However, if you were standing on the surface, you'd actually be in a field that's an appreciable fraction of what we're sitting in now.
Most
if you were
likely
in one of the strongly magnetized regions.
So
So they're
regardless,
very strong,
they're strong.
for a bar magnet.
And it's not because the rocks themselves are more strongly magnetized on Mars, it's because the regions that are coherently magnetized in one direction are much larger on Mars than they have to be.
Well, there's an ambiguity between strength and size of the source, so
There is.
we can't say for certain unless, we have pick up samples.
Can't say for certain, sure, okay. Still pretty sure.
Scientists never agree.
Yeah.
Yeah,
Was it Leonard? Or was
I just had a quick question about it. I thought I've heard it go by, and maybe missed the switch here somewhere, but what's the synergy with Mars Express, I mean, in MAVEN? Are there things happening there that
Yes.
are going to be coordinated, and who's mission control on that?
Great question. So the powers that be on each spacecraft, and that's Bruce Jakosky for MAVEN and a scientist named Olivier Vatas at the European Space Agency, who's responsible for day-to-day guidance and operations of Mars Express. They had a conversation, an email exchange, and decided that the two spacecraft should investigate ways of working together, making joint observations. And so each spacecraft delegated 3 scientists to start interacting. We started interacting at the beginning of June, I would say. And so the 3 scientists for the MAVEN team are myself and Rob Lillis and Joe Grebowsky, and there are 3 for the Mars Express team. And so we interact every 2 weeks by telephone. We just flew back from Sweden the night before this meeting started, where we met with the scientists from the Mars Express team for a few days to discuss coordinated observations. So that's how it's going to work. Our group will make recommendations back to Bruce Jakosky and Olivier Vatas, and we'll see what coordinated observations we're able to pursue. I'm also happy to discuss the kind of science that we can do together, if you like. So there's one piece of science that's maybe particularly fundamental, and that is the idea that we have a spacecraft that's on an elliptical orbit. With MAVEN, sometimes it will be sampling the solar wind, the incoming particles that drive the system, and other times it'll be in the system itself sampling that system. But it's very difficult to do both at the same time on a spacecraft that can't be 2 places at once. And if Mars Express weren't at Mars, we have ways of getting at these drivers by measuring the system itself. But a good check, a good reality check, is to have another spacecraft out there in the solar wind making measurements while MAVEN is in the system, measuring the system itself. This is how we can correlate drivers with response. And so maybe that's one of the most fundamental things that the 2 spacecraft can do together. But we also have different types of observing campaigns that we've thought about. For example, you can imagine Stephanie is the sun, and Mars.
So jealous that Bruce got to do this.
And if Jasper is MAVEN, and if Mars is here, and I don't know why Joe is here, to be perfectly honest. Okay, yeah. That was in this context of the analogy. And Rob is Mars Express. You can imagine when the spacecraft are aligned like this, and particles are escaping from Mars.
Hey, Michael, you're not muted.
They will wash first over one spacecraft and then the next. So this is an interesting coordinated observation, is to watch the particles that are escaping as they evolve, as they leave the system. We can learn more from this about how they're accelerated. And that helps us understand the physical processes that are driving escape. When you understand the physical processes, you have a better handle of applying those processes in other conditions. So those are just 2 quick examples of that.
Jasper, your hands out again.
I'm on the wrong side of Joe, though. The MAVEN orbit stays inside the focus. I'm going to add something completely redundant onto that, which is that in space physics missions, it's always a problem having a single point observation, because you never know for certain whether as you pass over a planet you're seeing spatial structure or temporal variations. And so having 2-point observations really fundamentally important for unfolding that.
And I would also add that while there is some overlap in the instrument complements between Mars Express and MAVEN, for example, electron spectrometer, ion mass spectrometer, the Mars Express spacecraft also has a radar which can study the ionosphere and which can remotely measure the plasma density as it's flying over, and that could be it could be a very useful situation where MAVEN could be flying through the atmosphere, Mars Express could be looking at it from a distance, and so that would allow us to basically see more than just a single point measurement, because as Jasper said, MAVEN's only at one place at one time. So there's a lot of opportunity for coordinated observations and situations where the sum is greater than, well, the result is greater than the sum of the parts.
Well, one great aspect of Mars Express, its apoapsis is much higher than MAVEN. So it always goes out into the solar wind on the orbit at apoapsis. So there could be a continual monitor of the solar wind, where MAVEN's orbit's more compressed, and basically sometimes with the tail, we don't go out at apoapsis into the solar wind. So that could be a continuous monitor of the solar wind for us.
Is that data collected, or is that, are you talking real time somehow, or coordinated responses coming out of these? Are you just going to be able to pile through the data later on between the two spacecraft? Or?
Well, that's, our working group is looking into how we're going to share the data.
Okay.
But basically, taking observations from both spacecraft that are recorded at the same time or in close proximity in time, things like that.
But we may also have to, there will be some planning. It isn't just a matter of looking at the data after the fact.
Yeah.
For instance, if there's a particularly interesting conjunction between the two spacecraft on MAVEN, we may only have a week or two to decide we'd like to download higher resolution data from the MAVEN instruments for that particular period. So there's going to be planning involved.
So before, I just wanted to point out, Betty, you're leaving at 10, is that right?
Yes.
So if there are any questions specifically for Betty, now would be the time to those. So, I'm sorry, you had a question, John, did you?
Yeah, this is a little bit more of a big picture sort of question. You were talking about the challenges of getting an Aronimy mission or missions by any other name as Aronimy. And given sort of the long-term future that focuses a lot on future missions that focus more on Mars sample return, do you see MAVEN as sort of like a once-in-a-career opportunity to get this data, and how does that affect your planning and work on the mission? How often you keep your fingers crossed that everything's going to work?
Yes.
It's going to work.
This is definitely a once-in-a-career opportunity, I think. And if MAVEN is successful, certainly MAVEN will make new and exciting discoveries that are unanticipated. That always happens with spacecraft missions. But if MAVEN is successful at answering its top-level science questions, then I think we're going to have a very good constraint on what happened to the climate, at least at the top part there. And so I think the measurements that MAVEN will return will be relatively complete and incredibly valuable. And so for that reason, my fingers are crossed that MAVEN will be successful from the very beginning.
Any questions for Michael specifically?
Yeah,
So this is
Mike,
for you, Michael.
can you hear me, Mike? This is Alex.
Yes, mostly.
Okay, this is Alex Ritchie from Nature, and there's been some discussion here about how all the cool surface geology at Mars has occupied scientists, and there's been implications that maybe the atmosphere hasn't gotten quite as much love until now because of all the cool stuff on the surface. I wonder if you can just comment on whether the atmosphere of Mars has kind of taken a while to be loved because of all the cool stuff on the surface.
Well, I mean, it's hard to imagine anything more sexy sounding than Aronimy. Well, I think the answer to that is yes and no. I mean, certainly the missions that we have been sending have had instrumentation that's been following the atmosphere, even though the orbiting missions themselves had a different purpose. So it hasn't been ignored, but it has been taking a back seat to the missions, and it's good to see that MAVEN finally going and actually meeting the kind of second half of one of the major missions suggested by the decadal survey before this previous decadal survey. So I think that's good news, and we are getting some information on the upper atmosphere. I also suspect that as we get into more challenging times of getting larger masses to the surface of Mars, we do start a major campaign of looking for getting humans there in the future, that the atmosphere will become a major focus for those missions. So I suspect that there will always be some atmospheric measurements, if nothing else than to provide some margin to the next spacecraft going to Mars and trying to go through its atmosphere. But also I think that as we get a better handle on things, we'll be moving toward more synoptic measurements of the atmosphere itself.
Thank you. And can you explain the back, please?
Yeah.
That is Henri, and it just happened to be a cool looking bat, and we thought it would look nice in the living room, although some people don't like it.
Nice to meet you, Henri. Any other questions? Lisa, you had a question?
I have a question for Maggie about, we talked yesterday a bunch about the difference between what Curiosity is doing down on the ground and what MAVEN will be doing in the upper atmosphere. And you may have answered this and I missed it, but how do they connect? How do you know, if Curiosity climbs Mount Sharp and finds that it gets to the point where it goes from hydrated minerals to not hydrated minerals, how do you connect that to what MAVEN sees in terms of overall?
Well, again, Curiosity has two aspects of the measurement it takes that are related to the atmosphere. The first part is that it actually measured directly the atmosphere composition with SAM, and that provides us with a measurement of the well-mixed, the bulk of the atmosphere. That measurement, it's very good to follow on a seasonal, on a daily, follow the daily changes and the seasonal changes. And that would be actually a good input for MAVEN, because MAVEN will look at the escape over the changes over the seasons, but you want to know actually what's that state of the bulk atmosphere at that time. MAVEN will do it by doing a regular deep dip campaign to the area where the atmosphere starts to get in well mixed, but MSL will be providing also regularly that measurement over the course of its life. So that's one part of the answer. The second part of the answer is that MSL will continue, as it's climbing Mount Sharp, will continue looking at analyzing samples of solid samples of rocks. And these rocks, embedded in them, the fingerprints of the exchange between the atmosphere and the surface at the time when the rocks was formed. And so by analyzing these rocks, we will have some idea of what was the atmosphere at the time when the rock was formed, or when that part of the atmosphere got captured or sequestered in the rock. And so that would give some point of hints of what's the state of the atmosphere at those specific times. So since MAVEN will try to extrapolate to the past, you will have nice anchor points that you can correlate with.
Next question.
Just because I was intrigued by the response that if MAVEN is successful, it will return such a complete data set, answer a lot of questions. If it does absolutely everything it's supposed to, returns wonderful data, can you imagine, as has happened with so many other missions, it opening up some vast new mystery that we might call for another mission because of it?
There's one thing that I've learned in space physics in my time, is that whatever you design your mission to do, some most interesting things you find will be things that you didn't ever design or intend to look for. And I have every hope and expectation that that will happen with MAVEN too.
So what I would describe, I would agree with Dave that this is a once-in-a-career opportunity in the sense that it's a very important opportunity. I'm hopeful that this is not the last mission we sent to Mars during my career that would look at these issues, because I think it is likely that we're going to discover something completely unexpected, and it will open up a whole host of other questions.
Yeah, I mean, I'm glad you asked this again, because I've been sitting here thinking about my first response. Dan, by everything that I said, I have sort of two addenda. One is that if you have to have a once-in-a-career mission, isn't it great to have it at this early stage of our careers? That's much better than an alternative. That's wonderful. And number two, I think, as we've all said, that new science questions will be open, and those science questions will be compelling. And if science questions are compelling enough, I sort of trust in the system for mission selection. As faulty as it can sometimes appear from the outside, I sort of trust that compelling science receives missions. And if there's compelling science that comes out of MAVEN that hasn't been addressed, then I'm hopeful that there can be a mission in the future to address those.
And actually, to follow on that, you can have the analogy with the work that was done in astronomy on Earth. I mean, it started with missions like Dynamic Explorer that looked at big problems and tried to look at the picture as a whole. And as we start learning about the Magnetosphere of Earth, it brought new questions or more focused questions, and that was followed by more specific and target-oriented missions in the decades that followed. So I do believe that MAVEN will ultimately give us the broader pictures, but it's gonna raise more specific questions. And then that will need to have a more specific missions to address these subtopics in the decade that follows. So we'll always find a good reason.
We have to find a different term for one.
And while it's premature to speculate on what we're going to see with MAVEN and where that might lead us, one thing that's been tremendously successful in the Earth system is multi-point measurements, constellations of spacecraft like THEMIS and the MMS mission, which is soon to launch. So one could imagine something like 4 MAVENs flying in formation and what that would get you. Far in the future.
And of course, there's always more instruments you could put on a spacecraft, but you need to be realistic in terms of what could fit within your budget.
And schedule a better red box, though.
So I want to go back to this question about extrapolating to the past from current measurements. I just don't think I really understand how you can do that. I mean, I totally get how you can, watch changes in Martian atmosphere as CMEs come through seasons, all this kind of great stuff. But I really just don't understand how you can extrapolate back to the past from that.
Well, okay, so I think this problem can be split up into a few different steps. The first is as stated in the MAVEN top-level science goals, you have to understand all the different ways atmosphere is escaping today and how those escape rates relate to the controlling drivers, meaning solar wind pressure, solar extreme ultraviolet flux, solar energetic particle events and their frequency. In an ideal world, particularly if we did have 5 MAVENs or 4 MAVENs,
Why not 10?
sure. No, but even with 1 MAVEN, we will still be able to characterize that, if you want to call it a function, meaning escape rate as a function of the different drivers. You can, as Dave was saying, what happens when you turn the solar extreme ultraviolet up, as it was much higher in the early solar system. We're hoping to get times of high and low solar extreme ultraviolet flux, or EUV, I'll just use the acronym, to see how that alters the escape rate. Once you have this sort of multi-dimensional function of escape rates, you can then use what we know about stars that are like our sun, so-called G2 type stars. And we have a pretty good handle on what their extreme ultraviolet flux history is like, as from their early stages up until more mature phases like our sun is in now. So at least from the extreme ultraviolet flux, we really can extrapolate backwards in time. Things like solar wind pressure, solar wind conditions are a little bit more difficult because, as Janet mentioned in her talk, our knowledge of stellar winds and stellar magnetic fields is not quite as mature, but there's still reasonable things we can say about how much more frequent space weather events may have been. And so we can make a set of estimations as to how much atmosphere would have been lost under different types of scenarios, and we can maybe talk to the astronomers about which of those ones would be more likely, but we'll be able to make as complete a picture as we can given the information that we have in in terms of how much atmosphere Mars has lost?
Yeah, Planetary too in a different way. And I also want to bring in the isotope ratios to this, because that's the other big lever arm on extrapolation back in time. And I'm going to do it with an analogy, which actually we discussed offline yesterday a little bit. And it's the way that I think about it. And it's oversimplified. But if you had a pot of water on the stove, and that water represents your atmosphere for the planet, and the stove was turned on high so that that water was boiling. And then you change that dial as a function of time. Changing the dial is changing the external conditions over the history of the solar system. And we have some idea of how this dial was changed over time by studying sun-type stars in different ways. Okay, and we really want to understand how the water in that atmosphere was converted to steam and escaped out into the rest of the room. And we're doing that not when the dial was set on high, but after the dial has been turned down all the way to low. And we're flying over this pot of water and looking at the steam that's coming off. And we're using those measurements to understand how steam comes off the water in the first place. And if we can understand how that happens, and we have sort of the history of the dial, then we have a way of inferring how much water has been lost from that pot of water over time, period. But the second thing that we do is we look at the water itself, and we look at, and this is where the analogy is getting way too tortured, so I'm going to leave it now. We go to the atmosphere itself, and we look at the isotope ratios, and we say, hey, look, there's a lot of heavy argon, and there's not much light argon there. The light argon must have been removed to space because it's more floaty at the top, and it can get stripped away more easily. And by looking at the relative amounts of the heavy stuff and the light stuff that should otherwise be quite predictable in the atmosphere, you have a second way of not getting the escape rates as a function of time, but the total escape over time from those isotope ratios. So we can pin it from two different directions, basically.
Something that we haven't spent very much time at this workshop yet talking about is the role of modeling. But having good models to place the observations into context is also a really important part of this. Because if you can build a good enough model and match it to the observations that we get from MAVEN, which will be very good, of course, you can run basically experiments with that and look at different scenarios. And that kind of work is also going to be very important in getting this whole picture of what has happened throughout history, I think.
And you can also use these models to, in some sense, fill in the gaps, because they're not going to be everywhere at once, and there are going to be certain combinations of external conditions that may not sample, and having the physical insight that comes from these models will help us to sort of fill in some of those gaps in the parameter space of how atmospheric escape depends on the different control parameters.
Yeah, I would even go further. If we understand the physics of each one of these processes, the physics is going to include the inputs into it. We should just be able to adjust the inputs. If we understand the physics, there's no problem extrapolating back, and the physics will come from the models.
So we have a combination of empirical and physics-based extrapolations.
Can you extend that analogy by what happens if a comet comes by and takes a ladle out of the water?
That would be so cool.
Can you make that happen?
So actually, to take that more seriously, one oversimplification of that analogy was that we were only considering escape out of the top of the atmosphere. And these are the processes that MAVEN will study. But as Rob said earlier, you know, stuff's getting pumped in from the bottom through outgassing. You have stuff getting delivered from the top in the form of comets. And not only do the comets deliver atmosphere to the planet, but they take it away. So in this sense, putting the MAVEN results in context with all of the other processes that affect an atmosphere over time is particularly important as well. And that's something that the PI, Bruce, is particularly good at doing and has tackled those types of questions throughout his entire career. And can I please have a promotion?
We'll double your pay increase this year.
Oh. So how much more do I owe you now?
Ken?
I have actually the same question about how you're going to be able to to infer this loss rate. And it kind of goes back to what Joe just said about, what others said about understanding the physics. I wonder how easy it is you're going to be able to understand the physics, because David, what you said in your introduction was that this loss varies over the day, over the season, okay, and with the crustal fields changing. So I'm thinking this is going to be extremely difficult to answer this question. I wonder if you could talk a little bit more detail how you're going to come up with some average number when there seems to be such a varying loss rate depending on the day, the season, where you are in the orbit, over the magnetic field. So talk a little bit about that. Thanks.
Well, we know, I was just going to say, well, we know how the Martian orbit works. We know how the angle between the crustal fields and the solar wind varies throughout the year. So we will be able to characterize the atmospheric escape as a function of the different orientations, for example, of crustal fields with respect to solar wind throughout the year. But we can average that over the year. And so we can get an annual average loss rate. We can take that back in time, for example. Because we know that Mars has been in approximately this orbit for its whole history with small eccentricity changes.
Something that's extraordinarily important is a map that Bruce showed you yesterday of periapsis as a function of time, and how that track, basically filled in most of the space. And that means that we're actually sampling as many of those different conditions of Mars season and Mars orientation as possible. So that was a really important part of the mission design, because of what you just said. It's not going to be easy, but the MAVEN mission is really designed to do that.
And then just to follow up on both again, and this is stuff you've heard before already from other people, but I think organizing the measurements by the different drivers is the first step, but it's still challenging with the data alone. We believe that we're capable of doing it with the data alone, even organizing things into drivers loosely. But then critical to all of this is applying models as well. And if you can, I hate this phrase that I'm about to use, but if you can tune your model appropriately to the data, or at least have a model that reliably reproduces some aspects of the data, then you have more confidence in applying that model in conditions that you have not experienced with the spacecraft, and that gives you a lever for extrapolating back as well. And did Janet want to follow up?
Yeah, I wanted to mention, we talked about how you really have to get the escape rate high, much higher than it is today, to get a substantial loss. And we talked about the possible effect of the CMEs, the solar activity. So it may be that the rotation of the crustal fields is in the noise as far as variability is concerned. And what really matters will be our ability to understand these episodic storms of escape. And so it'll be a different kind of a problem than, there may be things that we can ignore in the end for practical purposes, because we'll never pin down the exact to the decimal place escape total. But order of magnitude may depend mainly on large things like the rate of CMEs and the impact of CMEs that we'll have to determine.
And Dave and I will be pretty sad if the crustal fields turn out to be unimportant.
Yes, they're so cool.
They're fun for other things.
You think it will take the whole year? Because you got a 1-year prime mission to determine this, or could you determine this in 3 months or 6 months? I'm just trying to get an idea.
So we've actually been exploring this, and I've been exploring it for ion escape. That's another MAVEN hat that I'm wearing right now. Is our science closure leader delegated certain pieces of that problem, and so I've been looking at how long it will take to get the statistics that we need appropriately. And if we don't care about the drivers at all, that's just ludicrous to say that, but if we don't care about the drivers at all, then with the MAVEN orbit, we believe we can get a reliable estimate of the average escape rate today in approximately 6 weeks, the first 6 weeks of the mission. So, and we have a 1-year nominal mission, so this gives us a lot of time to look at variation, to start separating that out into variations with solar wind pressure, variations with ultraviolet sunlight intensity, variations with the magnetic field and the solar wind. So we believe that 1 year will be sufficient to explore the parameter space that we need to explore.
But let me temper that 6 weeks comment a little bit, because we have instruments that make measurements that are not going to be instantly understandable. As good a job as we've done of calibrating the instruments, we need to understand how they're working in the Mars environment and what they're giving back. I'm anticipating that that will take most of the first 2 months. That doesn't mean that we're not taking data during those 2 months. We're going to have the data, but we're not going to know how to begin to understand it until a couple of months have gone by.
And my estimate includes perfect measurements with no error bars.
And what we're doing, we're starting to float the idea that we're going to have some preliminary results that we can talk about. Today, we think we're going to have some preliminary results that we can talk about after about 3 months. And I would not expect anything before that. And how long it really takes depends on how the instruments operate in the Mars environment. And we're not going to know that until we're actually doing it.
So nothing in HQ, too early?
No, nothing formal at AGU. We're aiming to begin to let results out after about 3 months.
So Janet and then Matt, Janet, Mark, and then Caroline.
Now, and the sun is unpredictable. We may have no significant events heading toward Mars in that first 6 weeks. We may have to wait, just, we don't know how lucky we'll be. But we have determined by watching what's happening on Mars Express and Venus Express that the events have to be large ones. It can't, there's a lot of CMEs that go off that are just kind of wimpy. They almost merge into the solar wind and they hardly matter to anybody. But the fringe, the high energy, vast fringe of them is the one that makes the difference, the ones that make the difference.
Our extrapolation back in time is somewhat dependent on getting the right kinds of solar events, which we do expect will happen, but this is a stochastic process and it's not a guarantee that we will get that.
I gather, how little I understand about the sun, we're at solar minimum. Does this mean that we're solar max?
We're right at about solar max now, and or we're approaching it. It's a complicated maximum. MAVEN will get there, will nominally have passed maximum, and be starting down the curve after.
Oh, my mistake. Wait, I was under the impression that the sun was not very active.
It's a
low
solar
minimum
max.
compared
Yeah,
to-
it's a low max.
Low max, I'm sorry.
But also, historically, some of the largest events have happened on the declining phase, so we're hoping to catch some
Okay,
of
you
those.
guys will look out then.
Yeah, it's worked out. This is the ideal time for us to fly. Cool. Other than 11 years ago. when-
Yeah, I was wondering where were we in the 11-year cycle. I was trying to figure that out.
Yeah, it was a really great 11 years ago.
And Caroline, did you have a question?
Yes. Yesterday Bruce was showing us the little strips of the orbits, and I noticed the deep dips were processing around at different places. Was there actually an effort to coordinate those deep dips with specific geomagnetic or geophysical features?
More so with specific locations relative to the sun. So like terminator, subsolar point, night side, poles. Mars, of course, will be rotating around very quickly, and actually we'll get multiple passes for each deep dip. So we'll actually see different parts of the surface during each deep dip.
There are 25 orbits per deep dip campaign, so we should get a good sampling of the different planetary longitudes.
The 5 deep dips, which shows one, we wanted to be at the terminator because that's where we make our items. One, we wanted to be at midnight because no one's actually worked at the atmosphere at night down low. 3, we wanted one in the polar cap. 4, we wanted one in the subsolar region because all the Mars observations, there are no observations exactly in the subsolar region. And the 5th requirement was to have something in mid-latitudes in the southern hemisphere. So we actually passed the anomaly regions and come back to space. That was one of the requirements.
So when Joe says anomalies, that's also another term for the crustal magnetic field.
Okay, those are two equivalent terms.
Can we talk about the renewed controversy about whether magnetic fields are important?
Yeah. I would love to. When do you want to talk? Yeah, so I think it's a reasonable assumption to think that a magnetic field protects an atmosphere, especially from the solar wind, charged particles coming from the sun, because magnetic fields turn charged particles. So if you have a big global magnetic field like Earth does, it's useful to think of that as a shield for the atmosphere that deflects the incoming solar wind around the planet, like a big sneeze guard, essentially. And if you take that sneeze guard away, the solar wind goes crashing into the atmosphere, and you can splash atmosphere out. It's like throwing little pebbles into a child's wading pool. If you do it for 4 billion years, eventually you're going to splash all the water out. And so this idea is that magnetic fields protect atmospheres, protect them from the solar wind, and that they can be helpful for habitability. There's a competing idea, and to be honest, I'm still count myself in this first camp that I just described. But I think as scientists we have to entertain and address all reasonable ideas that are raised. And so there's this idea that sounds reasonable as well that's been raised, that when you deflect particles coming from the sun, you're changing their momentum by changing their direction. And momentum has to be conserved. This is a law of physics, that momentum has to be conserved. Where is the momentum that those particles might be losing going? It's going into the magnetic field that's deflecting them. And we could be talking about momentum conservation or energy conservation. Regardless, you can instead of thinking of the magnetic field as a deflector, you can think of it as something that's interacting with those particles and getting energy from those particles that then is transported along the magnetic field lines down into the atmosphere. And you're depositing extra energy into the atmosphere. When you deposit extra energy into the atmosphere, that energy can be going into increasing the escape rate of particles. So the idea has been raised that magnetic fields not only are not protective shields for atmospheres, but by the sheer fact that they're larger than the planet themselves, they're big energy collectors for atmospheres that collect more energy than that planet otherwise would have received from the solar wind. So this is the idea that's been raised, and there have been a few observations at Earth that have been presented in support of this idea. And I think it needs to be investigated, and it's useful to investigate it. Where this idea might break down for me is not in the fundamental laws of physics that we described in this whole chain, but the idea that the extra energy that this magnetic field collects necessarily goes into driving atmospheric escape. You can get extra energy, and that energy can be deposited in the atmosphere, and it can do any number of things. It doesn't necessarily have to increase escape. And so this is something that's entirely addressable with observations made by different spacecraft at Earth and Mars. But I think Mars is an especially appealing place to me to investigate this idea, because Mars has regions that are magnetized, and it has regions that are unmagnetized on the same planet that are interacting with the same solar wind at the same time. It's a little hard to compare Earth to Mars because they're in different places experiencing different conditions. But because Mars has magnetized pockets and unmagnetized regions, it's a great place to address this idea that's been raised.
What other things could the deposited energy do?
But deposited energy can go into heating particles, just increasing their motion, making them flow, things like that, but not necessarily giving them enough motion or flow to escape the planet.
Energy also doesn't have to stop at the planet. It can go back out into stuff in space.
That's true too. Yeah, it doesn't have to be deposited in the atmosphere as its final resting place.
Michael, did you have something to add?
Yeah, I was going to ask if this also holds true for galactic cosmic rays.
Ooh. Jasper?
Yeah, go ahead. I mean, the magnetic field certainly shields us from GCRs to some degree. I mean, that's definitely one nice thing that the magnetic field does for us at Earth. How that relates to atmospheric escape, I think, is much less certain.
Yeah, though, I mean, yeah, go ahead.
So, I mean, the atmosphere protects us from GCRs and that stops them, but GCRs are of such energy that the heliospheric magnetic field can deflect them. I'm not certain that the geomagnetic field makes too much of a difference to particles that are, tens of GeV, those sorts of energies, right?
Maybe not those energies, but
Yeah.
I mean, there's a spectrum.
Sure, okay.
But with the precipitation of particles, the best observations we have at the Earth, when you have a magnetic storm, where you have more energy being dumped in the low region, you get enhanced atmospheric densities, you get neutral winds coming out because you're heating the atmosphere locally, so the atmosphere will tend to expand. So it changes the dynamics of the whole system.
Yeah, but I mean, it's a good point that's raised, that particles and energy inputs primarily come from the sun, but there are other energy inputs as well for an atmosphere. Galactic cosmic rays are incredibly energetic, and the Martian atmosphere is so thin, and the magnetic fields there are relatively weak, that they're not depositing a lot of energy up at the high altitudes where escape is proceeding, so they're going to go all the way to the surface and the near subsurface. But at other planets, it's worth considering the energy input from galactic cosmic rays.
Going back to the question about the effects of the remnant magnetic field, we have extensive models of the whole magnetospheric system. And right now they're beginning to put realistic magnetic fields in. And I'm not quite sure what the conclusion is, whether magnetic fields enhance the escape or impede the escape. But we have models, very sophisticated, that are looking at these problems right now.
Models don't all agree right now.
Yeah,
There are
yeah,
several different models from different groups, and they don't necessarily agree on that particular one.
Well, one of the problems is in the models, I mean, these anomalies, or the remnant field regions, are rotating with the planet. So the biggest one, it might be in Bayside at one point in time, but 12 hours later we get nighttime, so we have different impacts, there's a time dependency in the magnetic field effects.
I know we've talked about some of this, but I wonder if we could just talk explicitly about kind of comparative planetology and escape rates. So like, you say, okay, Venus has an escape rate, can you compare like the escape rates of, Venus, Earth, Mars, and then does this happen in the gas giants at all? Can you just kind of take us through the solar system and give us a sense as to like who's escaping the most?
We haven't had any Iran missions for those.
Oh, okay. But what about Venus, Earth, Mars?
Well, Venus, again, I was involved with this. We see escape. We saw escape in terms of the hydrogen-deuterium ratio, and we inferred that Venus at one time had a 3-meter ocean, depth of ocean, equivalent on the whole planet. And remember, Venus is much bigger, so that's more water than anticipated at Mars. And right now, Venus Express is actually seeing hydrogen being picked up on the front side and thrown out, energetic hydrogen. And this is where the water is going. I don't know what the escape rates are at the present time. But Venus is big like the Earth, so regardless of the escape rates, it's comparable to Earth's.
Okay.
Won't have much of an impact on it. It'll be billions of years before you lose the whole atmosphere.
Okay.
And the same thing on Earth with the escape rates. It'll take billions of years until we approach the Mars type of condition.
Okay, so is Mars kind of a preview of the fate of Earth's atmosphere?
Well, it's kind of comparative atmospheres. Earth has a good magnetic field.
Right.
Venus has none. Mars is in between. In regions it doesn't have some, and the other ones. So really, if you want to understand the physics of the interaction of solar wind and sun with an atmosphere, we have 3 great conditions to show us what's controlling what.
But involved with that, Joe, remember that Venus's atmosphere is 100 times thicker than Earth's. Mars is almost 100 times thinner than Earth's. They're also at 3 different distances from the sun. Venus, Earth, Mars. So you have a lot of parameters to try to separate out. And ultimately, you can't do it observationally. because there aren't enough observations and you're not able to observe it through time. So you try to make the measurements of each planet, understand what's happening, develop models that you can run over time and see what the integrated loss has been.
And there are certain escape processes that are much more efficient at one planet versus another. For example, there's a non-thermal escape process known as dissociative recombination when an O2 plus ion, which is the dominant ion in Mars ionosphere, it can recombine with an electron, and the result is two hot oxygen atoms, which, depending on, well, some substantial fraction of those hot oxygen atoms that come from that sort of reaction will have enough energy to escape Mars, but not Venus, for example. And so that's not going to be an escape process at Venus that's important. It is going to be important at Mars.
The interesting factoid, if you're on the surface of Venus, you probably weigh about 20 tons less because of buoyancy.
Not just buoyancy.
I mean, another, it's not really an issue, but another facet of escape rates is the different units which can be used to express them, depending on what you're interested in. And so sometimes you express things in terms of precipitable microns, for example. Other times you express things in terms of the total number of particles escaping from that planet per second. And other times you express it as the total number of particles escaping from a square centimeter of the planet per second. You know, it's a per unit surface area thing. And so all this goes into sort of indicating the different science directions from which people approach things, and also the different parameters that we have to keep track of. Not only distance from the sun, but size of the planet is important too. So even though Venus and Mars may have comparable escape rates in terms of total number of particles escaping from that planet, atmospheric escape is a more efficient process at Mars because Mars is a smaller planet. If you're producing the same number of particles as big old Venus, then comparing them using one set of units is not enlightening depending upon what you're trying to think about.
But it's a larger fraction of the total reservoir there at Mars, because Mars is less to begin with.
Can you talk a little bit about why Mars lost its magnetic field? I'm not sure we know much about it, but we'll talk about that.
I can take a stab at that. Well, there's a few different theories, and this is very far from a settled scientific question. But what Nick said yesterday was useful, that to maintain a magnetic field, you need to have a planet rotating sufficiently quickly. It needs to have a liquid conducting core, mostly iron, with a couple of other elements in there too. And that core must be convecting sufficiently vigorously. If those three conditions are met, you can have a global magnetic field, much like the Earth does, and the giant planets do. So the question about what happened to Mars's magnetic field has to do with how the interior evolved. There are various ways that you can build up initial Mars in a model that starts off with the core being superheated compared to the mantle, 100, 150 degrees Kelvin hotter than the mantle. If you can have the core losing heat sufficiently quickly, it will be convecting sufficiently vigorously to maintain a global magnetic field. Over time, the core will cool. If the core is no longer cooling at a sufficient rate, the core to mantle heat flux, which is the important parameter that people think, the parameter that's important for maintaining a dynamo. If that core to mantle heat flux falls below a certain level, dynamo activity turns off. So Mars could have lost its magnetic field simply because the planet cooled. It's a much smaller planet. It would have cooled faster. It's not that the core had to solidify. It's just that the rate at which it's losing heat to the mantle had to fall below a certain level. Mars likely still has a liquid core today. It's just not losing heat quickly enough to maintain a sufficient convection. A little wrinkle to that issue is how quickly it would have lost its magnetic field. There's two different kinds of dynamos that exist in planets. So are those there's probably more than two, but there's two I'll talk about now. One is called a supercritical dynamo, one is called a subcritical dynamo. Subcritical dynamo is a dynamo where the convection in the core is only sufficient to maintain the magnetic field because the magnetic field already exists, sort of a feedback. If you were to shut off the magnetic field, it wouldn't come back again. A supercritical dynamo is one where the convection is sufficiently vigorous that even if you were to get rid of the magnetic field would bounce back by itself. Mars probably was in a supercritical state in its very early history and then transitioned to a subcritical state. If it then lost its magnetic field, it would have disappeared very quickly. The question is what caused that to happen? It could have been a giant impact. There were some enormous impacts happening on early Mars about 4 billion years ago, and there's certainly models of impacts where the impact happens, it dumps a whole bunch of heat into the upper mantle, the core can't cool sufficiently quickly for 10 million years or so as that heat is dissipating. The magnetic field shuts off, but because it was in a subcritical state, the magnetic field never comes back. The dynamo is dead, and that's it. And so it's unclear exactly whether the dynamo died of natural causes, meaning just from cooling, or whether giant impacts might have killed it. So this is an open topic still, but the only observational constraints we have is that the dynamo probably died between 4 and 4.1 billion years ago. 4 and 4.1. 4.0 and 4.1. Thanks.
Lisa, did you have a question? Yeah, so we've been talking about comparing the terrestrial planets to each other and how they're all really, really different. And then we're talking about comparing our sun to all the other stars that are like it. And we said something yesterday about exoplanets and how we look at these like Earth-like exoplanets and how Earth-like are they really, because we have all these planets that look Earth-like or would look Earth-like from a distance. I don't know if this is the best question to ask you guys or if I should be asking solar physicists, but why are we so sure that we can just look at other stars and be like, that's totally what the sun was doing 4.5 billion years ago, when we can't do the same with planets?
What we need is an astrophysicist.
Or an astronomy professor.
So I could take a stab. Not use. So stars typically follow an evolutionary path, and this evolutionary path is set by the properties that a star has when it first forms. And if the star isn't too out of the ordinary, then we are reasonably accomplished at understanding the evolutionary path that a star will take. And so what we do is we look at other stars that are of similar type to the sun. And when we look at them, we can, based on observations such as their current luminosity or something like that, we can understand where they are on their evolutionary path. Are they baby stars? Are they old stars? Are they teenager stars? Where are they? And when we can establish where they are on their evolutionary path, then we can also study those stars in terms of perhaps their activity or how they're interacting with the interstellar environment to understand what kind of solar wind, what kind of stellar wind these stars are producing, what kind of extreme ultraviolet fluxes these stars are producing. And if we observe enough stars like this, we can actually piece together an evolutionary history of solar winds around G-type stars like our sun, or an evolutionary history of EU flux for G-type stars. And so there have been whole programs. One program is called the Sun in Time program. And the Sun in Time program is specifically designed to study sun-type stars and understand what the evolutionary path is, not just of our sun in terms of its internal evolution, but its evolution in terms of how it's interacting with the surroundings. And Janet may have a follow-up on that, because I think she's been fairly key in making a connection between the Sun in Time program and solar wind and stellar interactions with planets like Venus and Mars.
Yeah. But I think you said it well. There are people dedicated to this question. There are difficulties, as I said, of remotely sensing stellar winds as weak as the solar wind. Also, when you're observing solar activity, solar type activity from a distance, you're not quite sure when you see a flare whether it's been a CME. The details of the solar cycles, the details of, you know, the stars have dynamos too that are driving their cycles. And the dynamo is very dependent on the details of the interior. And even the way stars work is under intense investigation right now. You know, that's a highly related problem. Is we are part of our central star in our origins, and we're all tied to it still. And the evolution of the planets has been tied to it. And so, in a way, it's a coupled problem. We may reach a point where we completely understand what's happening in Mars, right? And we still don't know what's happened to the sun over time. So in doing our model extrapolation back, we'll still be reliant on that particular discipline to help us out. So we're not isolated in our endeavor here.
That evolutionary path is a Hertzsprung-Russell diagram. I believe that's what it's called. Okay. Okay. No. Okay. Yeah. That shows that. Yeah.
Is that the same question? Sorry. Do we have any questions for Michael?
Yeah. I have a question. MSL related, if you can answer. At the when you were at Cumberland, at the end of Cumberland, you dropped some more samples in Sam and Kent, and also now on the trek to Mount Sharp. I wonder if you could tell us anything about the results, or when we might hear some information about the results. Thanks.
Okay, so from the samples of Cumberland, one of the interesting things is that SAM still has a sample in its chimera, so that the rover is actually, Curiosity has done some subsequent measurements using the same sample, so it's one of those, it's ongoing because the team wants to tweak the gas chromatograph mass spec to look at certain regions as it does a run with the sample. So part of the answer is that after they took the sample and did a measurement, that was only the first time they did measurements on that sample. They've been carrying it around. The other is that the team actually has taken the opportunity, as now the rover is pretty much driving close to the time that it's able to do things, and been writing up papers. So I know there's a whole series of papers that have been submitted to JDR, for instance, that will expound on the results that you've heard about in the press. Bottom line is that Cumberland was in fact used to kind of confirm what we thought we learned from John Klein, and that is emphasizing that this is an area that did experience water of a relatively neutral nature and relatively fresh. So that's kind of the big story, and the nuanced discussions of where the actual regolith came from and that sort of thing are coming out in a series of papers. So I don't feel too comfortable saying any more than that, just because I don't want to take some of the PI's thunder. Did I answer all the questions that I wanted to answer?
I thought that's what you were going to say. So when might we hear the results? In a few weeks or a few months?
The paper's been submitted, so now it's more of how long the review process takes. But my expectation is that for Cumberland in particular, I'm not sure whether or not we'll hear more results at GSA in that particular sample. But I think by AGU that will be, paper should be accepted, and the different investigators are, I know a lot of abstracts have been submitted, and they'll be able to talk more in depth then. So that's the summary.
Tell us about observations of ice on Mars by MSL as well as MRO. Thanks.
The observations are going to be attempted, and I try to remember the date. It must be coming pretty close when we think that ISON's going to cross the water line. That's being done, every couple of weeks they're going to do observations as a comet, because Mars actually has a better view than Earth does right now. It will take a little while to process it, because I think this is particularly challenging for both the orbital and landed assets, and that they're not really designed to do this sort of thing. They're supposed to be looking at Mars. So I think that will come out pretty soon, because we want the information to help tune the Earth observations of ice on it as it gets closer to the sun and then goes through the perihelion and comes out the other side. So I expect as soon as we know those, know the measurements and reach some degree of the conclusion, that we'll hear from the Mars missions on that.
And Mike, what about the sighting spring comet close past?
Well, sighting spring is happening next year in October, and that promises to be pretty exciting. Right now, in all honesty, what we know about it and what sort of calculations can be done, the error bars are extremely large. And I know that, particularly with orbital assets, where we go anywhere from truly excited about what we'll be able to see in terms of just looking at the comet itself, and also cometary particle interaction with the atmosphere. That should be very exciting, and in fact, it may get so exciting that we'd be worried about our orbital assets and might have to turn them around so that their hardiest side is facing the material that's coming to Mars from sighting springs. I've seen some calculations, and because the error bars are very large, you can't get too worked up about it until you actually get some measurements made closer as the comet gets closer. But there is a significant risk to the spacecraft, and then whether or not it's a 10% risk, 1% risk, or 0.1% risk is something that we won't know for a while. So it promises to be quite a show if we're able to look at it.
Any update on when we'll reach Mount Sharp, you think, next spring, or when?
Well, it's kind of interesting. It took us about 1 year to go, a little bit under 1 year to go 1 kilometer. And just several days ago, we passed the 2 kilometer mark. So 1 month later, we're able to add another kilometer. And I know that if they didn't do it this last uplink, they're going to this coming week, start doing auto navigation. And what this is you tell a spacecraft, you tell Curiosity to head over to that rock or whatever thing you pick, but it doesn't actually have a good model of the terrain itself between here and there. And so with AutoNav, it actually uses hazard avoidance capabilities and imaging to figure out what is the best path to get from here to the target destination. So far, in terms of driving, what we've done is pick the path for the rover to take and kind of make it deterministic and plot it out for the rover and tell it to do that. And then as it's going along, its path doesn't quite match with what it's supposed to be doing, such as there's extra wheel slip than anticipated, that sort of thing, then it'll just stop moving and wait until the next stage command sequence. But with AutoNav, it is one of those things where it decides itself the best path, and we're just starting on that endeavor. As you might imagine, the rover drivers get very nervous when they actually hand over control of the rover itself to determine where it's going to go. But one of the things what the consequence of that is, right now we're depending upon the terrain, you're about 70 meters that you can have the rover go and know that you plotted safely the course that the rover is supposed to take. When you add AutoNav, then it becomes a power issue, in which after 70 meters, it stops and has to recalculate its path on its own and figure out what is the best path, and then go on for another 10 meters, stop, do some more imaging, make sure that everything's safe. And so then what happens is it can extend the distance that the rover can go in any one day. And it just ends up using, then the limiting factor is actually power, or if the terrain becomes a little too hazardous.
Right, so you've been testing it now, and you said, so next week you'll actually implement it? Is that what you said?
Well, we're going to, and the problem is it was one of those things where they plan to do something and then something comes up, and okay, we're going to have to punt that until after the weekend, that type of thing. So I'm not sure if they've instituted, if they tried it yet, or is coming this week, where in fact they're going to try the AutoNAV for real. So that's and so what that means is it means getting them out sharp is easier, and then it becomes more of a how interesting is the terrain that we're going across on the way. So we've already picked out several waypoints where the science team has agreed just from orbital imaging, areas that look of particular science. And then when we get there and start doing measurements, we'll have a decision process of, is this looking more interesting than we thought or less interesting than we thought? And so depending upon those answers, we could be there for just a few extra days or something bordering on a couple of weeks.
So Mike, just because we've got you, this is Alex Witzy from Nature again. Can you talk a little bit about the orbital assets you have now and what role you see MAVEN playing in the future? In particular, you've got some aging assets in orbit now. Is there a role for MAVEN becoming communications relay for future craft?
So, yeah, the answer is yes. I mean, we do have aging assets, and we are concerned that Odyssey, Mars Reconnaissance Orbiter, and also Mars Express, for that matter, will not be there at some point in time in the future as a communication relay. And this is particularly important when we get ready to send the Mars 2020 rover to Mars, because as you might imagine, that's at least 7 years away from launching and 8 years away from actually landing and having communication. MAVEN is equipped, has an Electra on board, so it is able to communicate with the surface, and but we don't want to use it as a communication relay. We want MAVEN to do its mission of measuring the upper atmosphere and escape and measuring escape processes. But it's nice, although Bruce may not agree with it, it's nice to have telecommunications in our back pocket where if we do lose other orbital assets, MAVEN will be a good backup. And in all honesty, if MAVEN ends up being the prime communication relay, it will be difficult to do all of the science that MAVEN would like to do in the coming years.
So can I follow up? Because this is really a big concern. Even if MAVEN, let's say MAVEN, it's going to be successful. It's going to be successful. But even by the time Mars 2020 gets there, MAVEN will be 7 or 8 years old. So I'm thinking you're going to have another orbiter sometime. I know it's not in the plan, but can you talk a little bit about that? And you want to do NSR too, so you got to have it.
So it's understood that we are that we have aging orbital assets even by the time that 2020 gets to Mars. And there's a little bit of a calculation of the probability of any one orbiter being there may not be that great, but the probability of one orbiter being there among 3 is actually not bad. So it's a good bet. I'll put it that way. One of the things that we will be doing is including direct-to-Earth communication. We are looking at aspects of that capability to actually improve by on the order of something like 8-fold what we can do directly from the rover to Earth back. So we're using that as an assurance to make sure no matter what happens, we're going to have communication capability for the rover. In terms of an orbiter in the future, we recognize that at some point in time we do want to put in another orbiter. We're just not talking it right now because we are not in a budget environment that we have any hope whatsoever of starting the process of developing a rover right now. And we have some time to do something about that in the coming years.
Could I actually ask, it's a silly question that bears on this. I didn't realize you had to have relays in order to talk to a rover on the ground. Is it just the antennas can't handle directly from Earth to a Curiosity, you need some kind of relay in orbit?
No, direct to Earth capability is there, and the main drawback is that it takes a lot of energy and the communications are limited. So using a orbital relay saves a lot of power on the rover itself, and also the periods of time in which you can relay information are greater. Yeah. So there's a real advantage to be able to use a orbital asset to aid in the communication. There's also an issue of visibility with Earth, so that if you have more restricted times of communication capability also.
Hi, this is Lisa Grossman from New Scientist, and a question for Michael. Can you talk about what the plan is for figuring out how to get the cache samples back after the 2020 rover collects them?
What plans are there for getting the cache sample back? We've actually been looking at this for probably close to a decade. And it's recognized that there's several different ways you can skin that cat, so to speak. So what is being done, since we don't have on the books a orbital mission for the return, what we're doing is designing the cache such that it is easily retrievable. And part of the thought is that the rover can drop it off in a convenient place so that any future mission can go and get it. So the real thing that we're doing now is making sure that we understand future requirements such that the cache that we're designing now will not end up creating an impossible requirement for the future mission that will collect it. So we're mindful of that and working through requirements that actually translate through to future missions beyond caching itself. And I think we have a reasonable handle on what the requirements will be, and not put too onerous requirements on future missions to enable this cache to be retrieved when we come to the decision to retrieve it.
Can you go into any more detail about that? What are the options?
There's always been the just go and get it and come back. And there's a hazard of how do you pack all of that into one mission. And it's, in the grand scheme of things, the total dollars may be less, but the dollars spent in any one year may be excessive. So another aspect is what you do is you send a Mars ascent vehicle with a little fetch rover that will get your cache and put it on the ascent vehicle. And that ascent vehicle would just put the cache in Mars orbit for a different mission that would retrieve the cache that's in orbit and bring that home. Besides spreading out the total cost of doing this, you have the advantage of you have a couple of different stable states where the cache can be where it is until the future mission is sent and accomplished. So the cache can sit on Mars for quite some time before anybody goes and gets it. It can also sit in Mars orbit for a while before anybody goes and gets it. So besides adding kind of timeline flexibility to the whole sample return, it also actually splits the needed parts into different parts. And so one of the possibilities is that we will have an international partner who will take the lead on one aspect of the mission, such as the orbiter that retrieves the cache and brings it back to Earth. And so that's where we are with our thinking. It's not, that's not required, but we're just making sure that we're designing the mission now that doesn't preclude what our future options are.
Thanks. Any other questions for Michael before we let him go?
The direct-to-Earth communication for the 2020 rover, will that be laser communications? I know you're testing that on LADI coming up.
Yeah, that's a good question, and we kind of looked into it, and the real answer, if you want to do laser communications, is that you want to do it on an orbiter. As you might imagine, with the issues that we've had with our cameras on Mars itself, and I guess a great example is looking at the dust panels of opportunity, the solar panels of opportunity. The problem with laser communications from the surface to Earth or to an orbiter is you're in an atmosphere, you already have an atmosphere around you, and also you're in a dusty environment. And so then you run into all sorts of other issues with the efficiency and performance of laser communication. Plus, your slew rate has to be within a certain capability. So we have been thinking about laser communication for Mars. In fact, at one point in time, we had a laser communication mission that we were planning on sending to Mars. But doing it from the surface adds another dimension in terms of complication. And so that's not, at least right now, being really contemplated.
So what are you contemplating as for direct-to-Earth?
Well, so this is, right now, we don't have another orbiter going to Mars. And depending on how LADI performs and that sort of thing in this communication, that would be under serious communications for the next orbiter that we send. But we don't have plans right now to send another orbiter.
Neil, do you have a question? No. I thought I saw a hand go up.
I waved.
Oh, you
I thought he was recording.
Okay. Any other questions? We should probably wrap up unless there's something burning for Michael.
Actually, I'd like to ask a question that's not related to Mars. Is that off the table?
Sure.
Okay. There's been hubbub, at least in the last year or so, about whether Voyager's leaving or it's not leaving the solar system. I don't know if this is something any of you guys feel you can speak to, but do you have opinions on where Voyager is?
Which Voyager?
The first one.
It's up there someplace. There's many different possible plasma boundaries that Voyager could pass. There could be different indications of how much further it is, or how close it might be to completely undisturbed interstellar space. And I know there's the termination shock and the heliopause, and I think there's evidence that it's crossed one or both of those, but not the final boundary into interstellar space. That's to the best of my knowledge, at least.
I'm not close enough to those data to say for sure what I think, but I do know from my experience studying data from Venus and Mars, boundaries there, that trying to tell when you've crossed some boundary immediately after you've crossed it is incredibly difficult, and that usually it takes some time after you've crossed that boundary to realize what you've done.
Well, there was a very clear signature in the solar proton flux where it fell by an order of magnitude in the space of only a month, and it didn't go back up again. I know that that was thought to be a signature that they had definitely crossed one of the plasma boundaries.
So, thank you, Michael, for joining us.
Well, thank you very much, and I appreciate the time, and I'm just sorry I couldn't be there in person. It sounds like you guys are having way too much fun.
Having a lot of fun, lots of questions. So, round of applause for our panelists. So long, Michael, thank you.
Thank you.